Go ahead.
Okay. Yes. So there are a couple of things. One of them is we'll continue our work. We are looking back at the history of physics. So we start earlier, and one of the things I think I have shown is this equation. Maybe if I can show it again. So this is one of the things we'll continue. I think you have your.
Oh yeah, do show us that equation again? Yeah, put it up on the screen because it's good to have a record of these things.
Okay, so you have this equation. Can you see now?
Oh, hang on a second. And then I can lay it. There we go. So there's a slight echo on your side. It's
there's a slight echo.
Yeah,
when I put
sounds pretty
now
cool.
I think
but,
it's a little better, right?
Yeah,
better.
Yeah, it's much better now. Just run through those equations again and put them on screen.
So I just
if you could.
Yeah, it's a start of.
Oh yeah.
Yeah. Classical or Newtonian equation. This is one-dimensional. So the force is written from the Newton's law that F equal to ma, and a is nothing but second derivative of the position with respect to time, d square x over dt square. So the spring equation is that the force is proportional to the distance moved, inversely proportional. So that is minus kx, written as F equal to minus kx. So when we equate the two together, we get md square x over dt square equal to minus kx. And then I can write it as d square x dt square equal to minus k over m x. That's simplification. And then I transfer it to this side. So I get d square x.
Just move it up a bit. Yeah, nice.
Yeah. So I get this differential equation, d square x over dt square plus k over m times x, 0. When I solve for that, one of the solution is x equal to a sine omega t. That's a normal solution, right? We can also add another term for cos, but we just leave it as a sine omega t.
Yes.
It's classical solutions. So then I find dx by over dt, and that is a omega cos omega t. And then the second derivative, d square x over dt square, is minus
a, which is the amplitude,
minus a omega square sine of omega t. So when I put these, we have put this back, substitute back in the equation. Then we get d square x is minus a omega square sine omega t, and then k over m, x is a sine omega t to 0. Then we have a and a cancel, sine omega t is cancelling. So only thing that's remaining is, so we have only this term remaining, right?
Yeah.
Minus omega square plus k over m equal to 0.
So then that can be
and then
k over m could be equal to omega squared
m. And then we have square. Omega is actually we should write plus or minus k over m, but it's taken as positive, right?
Oh, okay, yeah, very good.
So that's how we get this equation.
Yes. So this is the general method,
clear, right?
Yes.
Yes. Okay. So then we are adding extra term here that normally equal to half me square, but we are adding k square over 2. This is the potential energy. So this is your potential energy.
Oh,
this is your kinetic energy. So when we add these two, again I convert to v square is dx by dt, the whole square. Same thing, kx square over 2. Then I differentiate to find with respect to, so f is nothing but del E by del x, right? Differentiate with respect to x, I get force. So when I differentiate, I get 2 times dx by dt. And then here x squared is 2kx.
Yeah.
So that's a simple differentiation.
And is
Then
that
I
2
can
over
write,
2, which would be just kx? Oh, yeah, that's what you're talking.
yeah.
Yeah, go ahead. Yeah.
Simplify that. When you simplify that, we get 2 and 2 cancel here.
Yeah.
And the 2 and 2 cancels. The 2 and 2 cancels here.
Yeah.
So I get simply m d square x or dt square plus kx. So
Right.
that's the equation I get.
Hmm.
And
Okay, interesting. dt.
yeah. So then what I did is that we have an additional force because of the so this is our main force. And then we have additional force because of the spring. So force with a PE, with potential energy, and then you have spring force. So these two terms, now we can equate md square x or dt square plus kx. That's with the potential, and that's equal to minus kx. Then we transpose is here, plus minus kx become 2kx, right? So this is the differential. This is the differential equation. Differential equation of force with PE, potential energy, and spring added to the kinetic energy. So the total thing what we get is this one.
Okay.
Right.
Yeah. Slide that up again, as just so we have so we can see the whole page.
So then the same thing. I simplify that. I take m. M is not equal to 0, so I can divide by m. So m not equal to 0, I have to say, okay, to divide this. So these are classical cases. So we don't worry about a relativistic yet. So d square x by dt square plus 2k or m times x. Again, the same solution. We go through the same kind of thing that we did before. X equal to a of some. That's a derivation, same thing. So then I have dx by dt equals a omega sine omega t, right? And then I have d square x by dt square equals should become cos omega t. So this becomes minus a omega square sine omega t. Okay, so that's d square. So now I can substitute here. So d square is equal to, so I substitute here.
Yeah.
So I get minus a omega square sine omega t plus 2k over m times a sine omega t equals 0. So I simplify that. I cancel a and a. I cancel the sine and the sine.
Yeah.
And I get simply minus omega squared plus 2k over m equals 0.
Yeah.
And that leads to omega squared equal to k over m, right?
Yes, of course.
And then I take the square root again like before, plus or minus square root of 2k over m. And normally we take only the positive value of the frequency.
Very good.
So,
Nicely done. I mean, yeah, you can kind of see that anyway, can't you? Because the only difference between this equation and the last one was the number 2. So
yeah. So if I compare these two, you see that we can see that. Let me see. So I have this equation. And then I have this equation. You see the difference between the two is just the square root of 2.
Yes. Okay, so you're thinking that might be the difference between the periods of the two wave functions we have. The initial wave function is the I guess it's wrong to call it a mass wave function, but if we're putting in position and mass into the Lagrangian equation, or not the Lagrangian equation, but you know what I mean, the equation that we're using there, and then out of that we're getting the momentum. So it seems like the second sine wave is the momentum wave, which could be you're thinking what period is maybe the square root of 2 times the other one.
Yes. Yeah. So that's something we have to figure out. But essentially, I'm just converting it to frequency. You know, the frequency.
Oh yeah. What are you doing there?
So the frequency is omega equal to frequency omega equal to pi nu, right? Where 2 pi nu is the frequency. So this is the frequency.
Yeah.
And this is the angular velocity.
Oh, okay.
So that's the that's the connection between omega and the frequency and nu, omega and nu. It's a very simple relationship. So we get for the first one, we get this relationship. So nu equal to 1 over 2 pi square root of k over m when we have no potential energy. It's a simple harmonic motion. And then when we have the potential energy, because of the spring-like potential energy, we get again 2 pi nu, we get this equation. Again, it's the same thing. So we compare these two nu together, nu 1 over 2 pi square root of k over m. Here is nu equal to 1 over 2 pi square root of 2 k over m. So just a square root difference. So difference difference factor is square root of 2. That's all. Between p equal to 0 and p equal to, and then pe equals half kx squared, over 2. Yeah. So this is the square root of 2 is the difference.
Yes.
Is that clear?
Yeah, that's very clear.
Yeah.
I think what we looked at last week was interesting, but so see the way you can kind of manipulate equations on the page very easily. I think I brought this up last week as well. But with the difficulty with the computer programs is that they're static. You know, they can't manipulate them themselves in a sense. Once what you've written down is all that there is. Do you know what I mean?
Yeah.
Oh, there's a terrible echo there, Rajan. It's like
yeah, I had to switch off this one. I'll just show this one and switch it off. P equals kx squared 2 equals 1 over 2 pi square root of 2 k over m. I just want to wrap up. So it's clear. I think this should be very, very clear. Right?
Oh yeah, yes.
Yeah. So then I switch off this one now.
Great, thank you. That was very interesting. So so when we're dealing with the potential energy, you know, within the system, it has to be well, there's a couple of things really actually that we could talk about. So when we talk about K, is this spring constant, yeah? So that's just a constant value. And obviously the mass is going to be constant in this classical system.
Yes.
So the mass could be anything. Let's say it's the number 3, yeah? Or something. And then K is also a constant. So K could be the number 4, yeah?
Yeah.
So then if we have the angular velocity squared is therefore, what did we say? 4/3, which is 1 and 1/3 is the angular velocity. So then the squared. So then the square root of that is omega, which is also then equal to 2 pi over. So then you can find out the period from that, because that would be you know, that times 2 pi would equal your period, right? Or is that right?
I don't know why your screen is not on. Anyway.
Oh, sorry. No, you know what's happened there is I think I highlighted your screen for when you were presenting.
Presentation. Yeah. Okay, that's okay.
There's all these different modes that we could have that we never actually.
Yeah.
Okay, so
I'm glad that we are going over this, because this is the fundamental thing. We have to get our feet wet on this one. You know, simple differential equation, and essentially all that rest of the things is just, you know, like manipulating that and make into operator algebra, where we define Lagrangian to be, you know, p square over 2m minus the potential energy, whatever the potential energy is, where the Hamiltonian is p square over 2m plus the potential energy, total energy. Lagrangian gives the difference energy between kinetic energy and the potential energy, whereas the Hamiltonian gives the total energy. And in fact, I'm manipulating that now in terms of conservation. So we good that we are talking about it, because, you know, if I can show that. So I don't know. I mean, it will show some echo, but do you want me to continue with that? Let me just write down and quickly show.
Yeah, sure. I mean, the echoes, it's not too bad. It's just, I think if we're talking back and forth, it might be more of a problem.
Yeah. Using transforms. So we have first let me write down. So
sure.
And then I can explain. So the Lagrangian.
Do you want to turn the camera on to do this, or?
Yeah, I can show the camera also when I'm writing. That's a good idea.
Yeah.
So that we'll follow along. Probably easier, you know, almost like a board, you know. So that's a good thing I like about this. Yeah. So can you see now?
Yes, I'm just going to make it, what's the word? Big screen, so that everyone can see.
So you have Lagrangian. L is defined as Ke plus Ke minus Ke, the difference between kinetic energy and the potential energy. And we know switch off this mic. All right. So we know that the kinetic energy is nothing other than p square over 2m, where p is the momentum, m times v, right? So then we have the kinetic energy is half mv squared. So that is nothing but we can write it as mv square over 2. And then we multiply it when we say p square. So p square equals m square v square.
Yeah.
Right. So then I have to divide by m in order to get mv square. So then p square over m becomes mv square, right? So I can substitute for mv square as p square. So I get p square over 2m, right?
Oh, yeah.
Okay. And then the potential energy, whatever, I think normally it's taken as V or something, depending on the convention. Either V or phi.
Or U, yeah.
The potential energy is V or phi. I think that's a symbol that's used.
I think they can. You can use. Oh, are you talking about Lagrange? You know, you can use TU as well, T minus U, but
T or T. Yes, T may be better because
no,
V we may confuse with velocity or volume, right? So T.
Well, T is for the kinetic energy, and then
Oh,
U,
T.
capital
Yeah,
U or V
Sorry.
can be the potential.
So I have T minus U.
Yes.
So that's my Lagrange. My Lagrange, let me write it here. Lagrange is T minus U, where T is the kinetic energy and U is the potential energy, right?
Yes. Oh yeah. Or K and E is good as well. Yeah. Oh yeah. No, sorry. Yeah. K E and then minus P. Yeah, is another way of doing it. Yeah, of course.
Yeah. So Lagrangian. Yeah. Okay. So now, if I use all that, I got p square over 2m, and then I put back in the Lagrange. P square over 2m is the kinetic energy. Then I have minus u is the potential energy, right? So this is a normal Lagrangian.
Right.
So
Yes.
this is a Lagrange equation. Now I have equation of motion with the Lagrangian. I get actually I'm putting in the new paper or a little bit of information about this. So the equation of motion is it's actually very similar to Euler. Lagrange equation is called del. Sorry, it's a full differential. Sorry, with the time it is full differential. Normally it is written d over dt. Del L by del. I call it Q. I'll tell you what that Q prime minus del L by d del Q equals 0. So now,
0. Yeah.
actually, it should be X. In our case, it is X. So Q equal to X in this case. Q is a position.
Yeah.
Parameter. And T is the
Well, this is the
time.
Lagrangian equation, isn't it?
Yeah, it's a Lagrangian equation.
Right.
Equation of motion.
Oh, that's great. I was just going to ask you about that earlier, but that's fine. So it's the equation of motion as well. Yeah, interesting.
It's also conservation. Uses conservation.
Yeah.
Conservation law. There is a derivation for that. We are not going to go into. I mean, you can get from Wikipedia or Wolfram. It's actually fairly
It's no
simple.
problem.
It's not.
I think I have that anyway.
You can actually derive from here also. You have to do a little manipulation. So
okay.
And so the Q prime is nothing but the differential of position with respect to time. So it's dq by dt.
Yeah.
Which is nothing but the velocity.
Yes.
So q prime is velocity, q is the position. So let's say q equal to x. If q equal to x, then q prime equals dx by dt, which is v, which is the velocity.
Yes.
So it's the same thing. So
when you're using
that
that
helps to manipulate. So it has some advantage. This is used.
So when you're using
Yeah,
that
this is
equation of
used in
motion,
if you go back, go to
there's a delay on
when you go to relativity theory, Einstein uses that. Can you see it?
Sorry, what did you say there? There's a delay on we're having cross chatter.
Okay, so let me rewrite that. So Lagrangian equation of motion, let's say.
Oh.
Is
Well,
what
the
we
question I was going to ask, Rajan, I was just going to ask a question. So the question I was going to ask was if L is equal to T minus U, that's just going to be a number, isn't it? So then you just differentiate that number when you use
now
the
let's
equation.
derive that. So this is the equation of motion. So let's put L equals p square over 2m minus u, and let's put q equal to x. So q prime equals v, right? The velocity. We have to be careful here because this potential energy. Okay. So then I put back here. So I put back in the differential equation. So d over dt, del over, okay, let me calculate del L over del Q prime. So which means that if I put back, I am doing p square over 2m minus u, and then differentiating with respect to the velocity. Remember that p equals to mv, right?
Yeah.
So it is good to change it just for the sake of it to half m squared. So then del L over del Q in our case comes del of p square is mv square over 2m minus u, right? So that becomes equals del over del v of actually m square v square, sorry. So because p square. So
Yes.
half mv square minus del over del velocity of u, right?
Okay.
So what happens here is that I can take minus half m because it's a classical mass. So m is, so in this case, m is classical mass.
Yes.
We don't worry about the relativistic and things like that right now. Classical mass, I can take it out. It's constant, right?
Yes.
So then I just get v squared. This should be v squared. Same thing, same v.
Yeah.
You have to be careful. And potential energy doesn't change with velocity, right? So that becomes zero. I think so.
That's because you're taking the
Although the
derivative, so it's
distance,
just zero.
yeah, in reality, though v is not a function of v, but in reality, position, u could be a function of position, right?
Yes.
If u equal to, so that's where the problem comes, I think, later on. If u equal to u of x is u equal to u of v, that's the question we have. But I don't think we have to worry too much about v square becomes half m times 2v over del V over del V becomes 1, right? That becomes 1. So it becomes mv. So this is nothing but a momentum. Okay. So what we find is del. So what we find is del over del q prime, del L over del q prime is nothing but the momentum. Right?
Okay. Yeah. So is that what we did last week then? That's what we attempted to do.
Yeah, we didn't do this last week. We didn't do the Lagrange. We did a simple thing.
Okay. All right.
We'll this is the next.
Maybe next week we'll do this. Yeah.
Yeah. So this is the beef. This is the main thing because this is what happens in relativity theory. Einstein starts with these kinds of things. So now in this equation, del over L or del Q prime minus del over del Q. So I had to find that also. What is del over del Q? This is position. So that's another thing we have to derive. I think it's good to derive these things because there's confusion. We don't completely. I'm going back to the blackboard essentially.
Oh yeah, I know.
So del L over del Q is nothing but again we do del m square p square over 2m minus 2u, and this is equal to q. Let's put q now. If q equal to x, the one-dimensional case, and then v equal to dx by dt, right?
Yeah.
So now I am differentiating with respect to x. So let me go to the next page. So I have del L del Q equals del over del Q over half mv squared minus u. And then I can take the each one. So I can take half m. Then I can do del v square over del q minus del over del q of u. So it's nothing but if q equal to x, and then v equal to dx by dt, right? Then we have del L, then del L over del Q equals, I'm just substituting half m del v square over del x minus del x of u. Is the potential energy. So that comes is we ask the is u function of x or no? We don't know.
We don't know.
Because the potential energy changes, when we move, the potential energy is going to change. So that's the problem we have to deal with. But let's simplify this. So half m. So now, in order to differentiate that with respect to x, okay. So we can do two things. I'm going to convert it to p square over 2m. So del v, I can change it to dx by dt, I think also. Let's try that. See, people don't do these kinds of things, but I want to do this because I think it's a simple fundamental thing. If we keep doing it, I think we should be able to reach somewhere. So del x by del t. Okay. So what is del over del x dx by dt squared? If we treat it like that, I'm differentiating now with respect to x. That's why the space and time comes. I think this is where the Mangosky starts working out, because you have both space and time coming into the picture here. So if I differentiate with respect to x now, I get 2d. I think I get, let's try this, 2 dx by dt. Then I have differentiate with respect to x. I get d square x over del x dt. Right?
Oh, because you're, what are you saying? Where are you getting the ds squared x over dx dt?
Oh, let me, sorry. The first, we have to do partial. We have to do, oh yeah, this is correct. This is correct. Because we already
No,
one
I'm
term.
not saying it's wrong. Yeah, I don't get the.
Very simple. If you have del or del x of, let's say, y, right?
Yeah.
First, we have to do del y over del x. Okay, we have to find the, okay, what is a y equals, let's say y equal to x squared plus 1, right?
Okay.
So del y over del x equals, and let's say y has a term y. Sometimes they may have another term z or something, but that doesn't matter because it drops off. So
Sure.
2x squared, and then this becomes 0. This also becomes 0 because del z of del x is 0, right? So the partial differential depends only on the variable. If the variable is not,
but am I wrong for thinking that when you take the derivative of x squared, it just becomes 2x?
2x. Sorry.
Yeah.
2x.
Okay. Okay. Yeah.
Becomes 2x. So del y over del x becomes just 2x. That's it.
Yeah.
The same way we do this here. In this case, y equals dx square dt square the whole square, right?
Yeah.
So here it's a little more complex. So del y over del x.
2 dx over dt is the answer.
First, we differentiate the whole thing.
So why did you give a second term of d squared x over dx dt? I just don't understand where that term comes from.
That's because,
yeah.
First, we just, okay, we have to substitute here. See, in this case, okay, let's dx by dt equals, let's put a value here for x, okay? That makes it easier. But if you want a general thing, let me get another paper. You want to get this straight now. Okay. So now, y equal to dx by dt the whole square. So now I can do a transfer of term. Let's dx by dt equals v. Maybe that will help. So then y equals v squared, right? Now I am differentiating y with respect to x. So this is what we have to understand. Here, v is a function of x, right?
Okay.
It's a simple thing, but it becomes, that's how it becomes a little complex as we go along.
Yeah.
A lot of things in the Wikipedia, they go over that, but they go to different tangents. You cannot, it's very hard to understand that. But we want to do it for fundamentals, you know.
Yeah, yeah.
So
See, I think I
the way
understand now.
the differential works is first we differentiate just what we have. So it becomes 2 times v of x, right?
Yeah.
But then we have to differentiate what is inside. So the inside is del v of x over del x. You see that?
Yeah, yeah.
We have to
Of
do it.
course. Yeah.
Okay,
Right,
that's
yes.
this is why it becomes little complex, but if you follow along,
Yeah.
this is the next step of calculus. That's a little complex, but once we get this little advanced, the next level calculus, I would say it's not the most advanced thing, the next level. So this is okay, right?
Yes.
Yeah. So now I substitute the value of v. I know v equals dx by dt, right? V of x equal to dx by dt. And now my del y or del x becomes 2 times dx by dt times del of, this is very complex, del dx by dt of del of x. You see that? We can also figure out from here what is del v of x of del x. What is that?
Well, didn't you just write it out? It was.
That's nothing as del. So let me put it here. We'll get this straightened out. dxt del of x.
Oh, yeah.
So when
you just literally wrote that out a second ago.
Oh, it's actually, yeah, we.
It's not a squared, is it?
Yeah, there's a square here. Sorry. Yeah, there's a square here. Yeah, there's a square.
Because the earlier term is vx squared, v squared.
Vx squared, yes. Okay.
Okay, so that's just coming down from the earlier equation.
I think this is okay, but I am getting to that. So now that becomes, here it becomes 2 v of x, right? Del of vx over del x, right? It's the same thing as that. That's good. This is good. And that is equal to, now how do I equate that? Yeah, that's simply we put 2 dx by dt. Now it becomes easier actually to see. You see that? Dx by dt over del x. Right?
Okay, so why did you have that squared earlier? Remember the one you scribbled out? Oh, because it's a different equation, is it?
Because it's half mv squared. You see that?
Oh, yeah, okay.
Yeah, the half mv squared.
You know, on the previous page, you scribbled it out, but it had, that term had squares in it. On the previous page?
Vx.
The equation in the middle of the page that's all scribbled out that we thought was correct.
This one?
No, the previous page. The page before this page.
Oh, previous page. So let me go back here.
See the equation in the center that you had that was correct. That's scribbled out. Yes. That one, yeah.
And this one, you mean this bit? You are here.
Yes, but that's d squared x.
We are going to get to that. We are going to get to that. That's what I want to. So now here, I have to find what is. Let's do step by step. So del of This is the main thing we have. What is this stuff? Okay. No way we can avoid this one. So I have to differentiate the dx by delta x, right? How do I do that? So let's go back to the fundamental. So we have del y over del x. We have that. And y equal dx by dt. Okay. So suppose I have y equals we can transfer the variable. So y dt becomes dx. Okay.
Yeah.
That's one way we can figure out. So now I have to differentiate both sides with del of x. So del of y dt becomes del of del dx. What is del of dx? Become d square x, right? So there's a difference between partial and the full differential, but I think this will work. Actually, it becomes, see, this is where I'm not completely sure, but people use it. Sometimes they use this as del square x. I don't know which one is more. So
Right.
this is where the problem comes. So
So
that's
you're
the
just
same
saying
thing
that
here.
you're differentiating the differential, so it becomes
Second
d
differential,
squared.
right? When we do
Are
the
you
first
saying it's like
differential,
the
second
second
differential
derivative
is,
then, or something?
yeah, we know the full differential. Let me get another paper. Yeah, I want to make it clear. So suppose I have d of dx of the second derivative I'm trying to take, dx over dt, right? It becomes d squared. No, second derivative, let's say with respect to time itself. So I get, this is acceleration, right? I get d square x by dt squared, right? This is the acceleration.
Yeah. Yeah.
And this is the velocity, right? And this is the time. So if you differentiate velocity with respect to time, we get acceleration, right?
Yeah.
That becomes d square x by dt squared. Suppose I'm differentiating instead with the space d over dx by dt. What do I get? I should get again the second differential, right?
Yeah.
But in this case, I have two one. I have dx also dt. You see that?
Yes. Of course. Yeah.
Yeah, that's how I getting that. So now I think we are clearing that. This becomes easier. Calculus is always confusing. When you go to little higher thing, we have to be very careful. The simple things. This is a very similar thing that happens in Fick's equation, many different places. We get space and time. I think maybe this is where Minkowski said that you have space and time coming in. And we have previously the Fick's equation comparing to Fick's equation. Of diffusion.
Okay.
So in this case, what happens is that the x changes. There it's more complex because your concentration, no, what is, let's say psi over dx by dt. So psi is the concentration. And d psi or dx is the gradient, right? Concentration gradient. And then d psi over dt is the flow rate. Normally the flow rate, right? The concentration rate of time rate of change of concentration. So it is connected with the flow rate.
Yeah.
So this is how we get this equation. And when we solve it, there's another side to it. We get the error function solution because you have both space and time. Yeah, at some point I want to talk about that. I think that's a very important. Like I mentioned before, this is what led to Minkowski, Einstein, space-time.
Oh, it's interesting, yeah.
Yeah. So this is why it becomes complex, and Minkowski came up with the 4D space-time.
Yes.
It's called the Minkowski transformation, I think. Which Einstein used. Because Einstein was his student, I think.
Yeah.
So this was a big famous Minkowski transformation, the 4D space-time. So this is the connection. I think once we are sure about this, we can move on. But that's where the Lagrangian comes into picture. And we are trying to derive the Lagrangian. So we go back here. Our equation of motion is del q prime minus del q. And we are trying to figure out, when you go into detail, we figured out that, and this is where it becomes little complex. So what is del over x? So yeah. So now we rederive that.
Yeah, shouldn't it be
I mean, that
over
derivation
dx?
actually is quite complex, actually. If you look
It
at
is.
Wikipedia, it is not simple.
It's a little bit
So now
confusing.
we have, so del L by del Q is same as, we are using Q as X, del L by del X. And L we know is half mv square. But only when I do like this, I am more comfortable, actually.
Well, that's good. Better to do the.
I'm still keeping it fundamental level.
Yeah.
Okay. So now I can equate that to half m del v square over del x minus del of del x of u, the potential u. I had to put a capital U. That's a potential energy. So this is the velocity. So now I substitute for velocity, because half m del of dx by dt. You cannot get around this. I don't know. Same thing comes up. Del x. Oh, that's why it is a little bit confusing. Okay, now we figured out that we have to do this stuff, half m. I have to do 2 dx by dt. First, I differentiate the outer one. I get this one. Then I have to differentiate the inner one. So then I get second term. So that becomes, I don't know whether it becomes del of, let's put it same as that, del of dx.
Wouldn't it be d to the 2x?
Let's put it like this now. Same thing. We'll do one more step.
Okay.
So del of dx over del of x. So I like to put it, this becomes, let's say you keep it simple, u of x, not a function of x. So then del of del x, u of x becomes 0.
Yeah, okay.
Right? I don't worry about that term right now. We'll come back to it later. 2 and 2 cancel, so I don't worry about that. So m dx by dt, I have this one. So I'll write it as del of dx. Then at the bottom, I have del x and dt, right?
Yeah.
So what is this one? Let's put it as dx by dt. This is a step we have to be careful. So this means I am differentiating with respect to x. So
does it just become dx over dt?
yeah, partially, I don't worry about the time aspect. Suppose x equal to x of t, del
Yeah.
x, del x becomes, it's not a function of t, it becomes constant. So del x by del, yeah, it becomes constant actually. So we aren't out to worry about the time aspect. Suppose, or let's put a y equals, let's say x squared plus t squared time. So del y, I don't worry about the time. It becomes 2x, the time aspect, because del t of del x equals 0. See that? So that's what a partial differential means. So del y del x becomes just 2x. So only if it is, so in this case, we have to still worry because still x and x. So I have to put it as square. So I think I have to put it as like that, I think. That's what I'm not sure. So let's substitute that value. So now this is our
right. Yeah, that seems.
I think that's why upper script, lower script, all these systems. Yeah, we have to let's proceed that.
Yeah.
We may have to come back next week to solve this completely.
Seems good so far, though.
Because it's not a simple thing. But I think we have to figure this out completely. I am all for it, figuring it out, because I'm doing that now, I think.
Yes.
I'm looking up things. Where is our original equation? Okay. Yeah, this is our original equation here. And then we have found out, so this is the first one. For this one. And then I have del over, I think we figured that out. I should have put the numbers in this. Let me delete in here. Normally I do that, but it's okay. Somewhere we figured it out. Yeah, it's right here. Okay, we figured that here we are derivation, right? We are derived here. Del L, we derived that del L, del Q. This was easier. Equal to the momentum P. Equal to mv or m dx by dt. So these two are the two things. So let's put back then our equation. Yeah, this is our equation here. So let me get another paper. You need a lot of paper. I mean, it's better to have, a fresh sheet of paper.
Yeah, no, you're dead right. Yeah.
Okay, so let's get a fresh sheet of paper. I don't mind this because I want to figure this out. So now equation of motion, you can see it. Equation of motion is d over dt over del L over del Q prime minus del L over del Q. I think that becomes 0 when it's conservation. So let's keep it like that.
It does, yes.
When you apply the conservation law, it becomes automatically that. And then I figured out, now let's bring it back and substitute the values. So now I have d or dt.
Oh, yes.
I'll rewrite L over del Q. It's good to write down. We figured out is m dx by dt. I put a question mark here because when we simplify, we may find some strange things, and that's where I'll put a question mark there. So, and then I have one equation I have, and then del L by del Q prime is P. So once I copy this, it's easier. Ex by dt. So I don't have to keep referring to that. Okay. So I have these two now. All I have to do is substitute this value here. So when I substitute the value, I get d over dt, and then del L over del Q prime is this one. Equals m dx by dt. This is why people use prime and things like that, but I like to keep it like this. The prime also sometimes gets confusing. So del over del Q is m dx by dt. This is laying everything out. E square x dx times dt. Okay. I'll put a question mark there because you are partial. Now I simplify this one. So m is constant, no problem, classical math. So this one is nothing but m d square x by dt square, right?
Yeah. I think so. I can't really see what you're writing.
Can you write? Can you see?
Oh, yeah. Okay, now I can see. Yes, so that's acceleration. No, it's force. Yeah. M times the acceleration.
So this is the actual Lagrangian, right?
Yeah.
This is nothing but d over dt of del L by del Q prime minus del L by del Q.
That's a minus sign, is it? Oh, yeah.
Yeah, there's a minus sign.
Okay, I thought there was an equal sign. I was getting confused. So
no,
yeah,
it's
then
actually
that's
minus. Sorry.
Yeah, I see.
It's okay now, right? Okay.
Yeah, definitely. So
now
the first term is equal to force. So you got force minus displacement. Is that right?
The force. These are forces.
Yeah. M times the acceleration minus
m times d squared x by dt square is nothing but ma, right?
Which is the force. Yeah. Minus
force F.
What? The displacement? Or minus the potential energy?
Minus this stuff. This stuff. What is that stuff?
What is it?
also should come to that. I think it's a manipulation
we don't know what that
of
is
that.
Yet, do we not?
See, in conservation, what happens is this now changes to m d square over dt square somehow. We can manipulate it.
Yeah. Okay.
And that's where the manipulation comes. I think that's why it's not simple. They don't show it like that because
you're saying it's a conservation thing. So does that become 0 then?
Yeah, it becomes 0 exactly.
Yeah.
Okay.
So we just have the force. So the force is conserved.
Yeah. This is where people moved away from fixed, because fixed would were like this way. But people ask this question: is this right? I think that's why Minkowski came into Minkowski space and everything. And the conservation, the conservation, what happens is, what is the law of conservation say? This stuff goes to zero because the del V of del x, I think, goes to zero. Sorry, not zero.
No.
Becomes the acceleration, right?
Hang on a second.
No, it's not acceleration. Sorry, it's not acceleration. So del V over del T is the acceleration, right? So and then this is nothing but so what we went originally. Let's go back to our original thing was good. So let me get another paper. Yeah, this is something we had to figure out. Let's show that what's going on. So go back to the original thing. I have this stuff. So I have del over del x v squared. Go back there. We get 2v del v over del x. Right. So that's a position. That's the velocity depend on the position. Is v a function of vx? We know v is a function of t.
Yeah.
So actually we have to do v of x comma t. You see that? So we are bivariate, two variables. That's how the Minkowski starts solving the problem. This x and t comes into picture. This is where our space-time comes.
Okay, but x and t have always been in the picture, haven't they?
Yeah, x and t. So I have to find del v. It's easier. Del v over del t. Now if I write that, del of v of xt, that's why we use partial differential. So now that becomes acceleration. I don't worry about the x, like partial differential.
Well, shouldn't becomes when in a partial differential, you're looking over multiple dimensions, yeah?
Yeah.
Like
so we don't worry about the other variable. Our other variable is constant. Partial differential. That's a good thing about partial differential. And del v of del x, I don't worry about the time aspect. So now, but what is the x aspect? Del v of xt over del x. What is this stuff?
Taking a partial differential equation over only one dimension.
Yeah, I think you go to higher dimension because space-time means you have x, y, and z. So now my velocity becomes...
You're not explicitly writing out x, y, and z. You're just writing x, is it?
Write that. Now it's explicit, right?
Oh, okay. So yeah,
this is space-time. Space-time velocity.
Yeah. That's no problem. I was just confused because you wouldn't do a partial differential equation over a single dimension, would you?
Yeah, because we want to keep it simple, one dimensional, but we have to extend to 2 dimensions.
Oh, okay. Yeah.
We see that why we have to extend, right? So it's called the 4-vector thing.
Okay, yeah. So, but in my mind, I was
X
just
is
thinking
actually,
of. I was just thinking of like the simple one-dimensional case to begin with. But yeah, okay.
yeah. So T actually should become also T also should become a vector actually. I think
Well,
that's
that's
what
fair.
we are
Yeah,
trying to do.
yeah.
4 vector.
T would become a vector, so then it would. Yeah, you wouldn't have it as 0. Well, what do you think?
It's not a
Will we
scalar.
go for? So how much do we have left to do here? I mean, just in the first section, are we nearly finished with the equation of motion, or?
Yeah. So now I substitute the value here. So when I substitute, I had the equation.
I'm surprised this is so. There's so much to this. It's one equation. It's quite. It's quite intense.
Actually, this is more laying out. We are just expanding it so we understand the whole thing.
Oh,
Fundamentals.
okay, yeah.
But
Right,
people
yeah.
use simple, simple tricks. They arrive at use prime and things like that. So
yeah, of
this
course,
is the equation we have. So the final equation, the Lagrangian, I call it Lagrangian equation of motion.
Yeah.
I think we can, once we figure out, I think we can understand a little more about what they are doing there. Is d over dt del L over del Q prime minus del L del Q. Because the Q in this case is a velocity we can use up to 4 dimensions. Q equals, let's say, x, y, and z and t, right?
Yeah.
That's why the Q is used. So that's
useful.
Okay.
Yeah, that makes sense.
So d over dt del over del Q prime minus del L over del Q. What we derived, now I had to change it to Q. This equation here. So M times
right. I get it now.
d square Q over dt squared, right?
Yeah.
Minus dq over dt d square q over dx dt. Now, again, it's a question because we have both partial and full differential coming into picture. That's why I put a question. I think that's why I use superscript, subscript, things like that, So we can use, there is something called q prime. This is called covariant.
Yes.
Tensor. And then we have q prime, upper script is called contravariant tensor. And then these two are connected by metric. There's a metric that connects them. So I think this is the correct one. I think you also know this. Some kind of a G mu times q prime of mu, something like that.
Oh, yes, of course.
So this is the metric. This is the metric tensor.
Yeah. I've learned about that. I'm not entirely sure of the connection between the two, the equation of motion and that, but yes, it's interesting. So you're kind of moving on into metric tensors now, or?
Yeah, we have to understand more about the metric tensor. I think we are moving along fine because these are little advanced. I reviewed a paper previously. That person, I think, I sent some comments. Once he finishes that, it probably will be publishing. Somebody from Russia.
Great.
And this one, he says this is preferable. He's proving it. He has a very detailed proof why this is preferable. So Q prime mu nu preferable over Q prime superscript contravariant. So this is a covariance. Why is it preferred over contravariant?
Oh, okay. Thought they were both useful,
So
but
that's
what do
very
you think?
advanced.
Should we have a quick break? Cup of tea
Yeah,
or
we
something?
can get a break, and then
Good man.
we can then wrap up half an hour to 1 hour. Some questions. We'll go over that. We want to ensure that we get this straightened out, before we move on.
Yes.
Because it's simple enough now, I think.
Yeah.
We'll discuss about that. Let's take a break now.
Okay,
Thanks.
cool. Back in 10, 15 minutes.
Can you hear me?
Yes.
Oh, can you? Okay. I was not sure. It shows he's lost some connection. Is to us showing, so it's okay. So
Yes.
we're discussing. I think it's quite important, right?
Yeah, it sounds very interesting. So I have a couple of questions though.
Okay.
So yeah, so before we got to the equation of motion, we were discussing things in terms of, you know, angular velocity omega and the
Yeah.
spring constant k, and then
Uh,
once we kind of transitioned into the equation of motion, I noticed that kind of disappeared
Lagrangian.
somewhat.
Lagrangian.
Yes, the Lagrangian equation. We sort of stopped bringing up the spring constant disappeared. So why is that? Is that because we're just focused on the momentum at that point? And
Now we are the instead of spring, we are generalizing it to potential in terms of the change in the potential energy, and specific form of potential energy is a spring constant kx.
yeah,
But
yeah,
you
that
can
makes
have different types of potential energy, and also the total kinetic energy. Also, we can have a general equation. We said p square over 2m, and people are extended this p square over 2m and include electromagnetic other things also. The momentum. That's why we have the upper script, lower script. We can have few. Yeah. Can I show this? Maybe I will show this again. We'll go back to the other screen.
sure.
Yeah, that's something I'm considering now. It's quite interesting, but there's a lot to be understood about that also. Oh, okay. Oh, you already put me in. Thank you.
Yeah.
Um, okay. So, got time. Let me get some few pieces of paper that I have.
So I see. So it's all of those terms are kind of
Yeah,
inside the Lagrangian. So
yeah. So let's go back, rewrite the Lagrangian equation of motion. Again, we have our famous equation d over dt del over del q prime minus del over. We are not okay. This is our equation, and now q is we said that q has to be q x y and z and t, right?
yes.
Again, the q prime. Now we can q prime when we do that. It's nothing but dq by dt. Now in this case, okay, this also becomes dq xyz t over dt, right? So now we have to worry about, suppose x and t are function of time, we have to separate it out. So this is where partial and full differential come into picture. So let's write it out, how that comes. This is the next step of complication, I would say.
Hmm.
Now I have to write this way. You probably know this one, okay? Del q of del t. Then I have to do actually no, we have to differentiate with respect to x. And then we
Oh,
have
dt.
dx
Yeah.
over dt. You have to do these kinds of things.
Huh.
This again is not very clear, but what we are doing, I think, clarifies, because we are again going back to fundamentals, and I like that way. Plus, these are fundamentals of connection between the partial and the full differential. So in order to do that, let me finish that, and then I will go back. The actual simplest thing is, I'm just showing you this one, dy by dt. The reason is the following. Okay, suppose I write q equal to q x y z x y z t. I simply find dq, the full differential, right? The full differential is nothing but del q x y z t over del x time dx, okay, plus del q. This is the definition. We are going back to the definition of the full and the partial difference. Again, it's the next level of calculus. It's not the most advanced, like I said, but it's not the basic level. It's little more.
Yes.
Partial differential equation. So dx y z t, to write the whole thing, del z time, this becomes dy and it becomes dz, and then I have del q x y z t over del t over dt. You see that?
Yes.
Okay. Now, if I find dq by dt, all I have to do is go into the thing. I don't worry about this one, because this one the same. Then dx by dt, right?
Yeah.
Then del q x y z t. Again, I'm keeping as Euclidean Cartesian coordinate, so it's simple enough.
Yes.
This is why when you change the variable, that's where you have the rotation, all those things come into picture. But right now, we are keeping it Euclidean and Cartesian. So let me write it here: Euclidean, Cartesian, space-time coordinates. So that makes it easier. Okay.
So you don't have to write the, like, if it's over del x, you don't need the x term in the dq, do you?
Where?
See, dq equals, oh yeah, any of those places where it's like dq x y z t. If it's over, sorry, del q, it's over del y, then that just cancels out the y, doesn't it?
That becomes 1, right? So this is how you can convert. This is your full differential equation. I think it's called full, or there is another term also. This is called the partial.
Yes.
Differential equation. So this is the connection. Whenever you do, this is you can go back to this is what I do. I go back to the fundamentals. Now, and the fundamental is this one. The most.
Is it ordinary? Ordinary and partial.
Ordinary, yes. Full or ordinary, called ordinary differential equation. So this is the ordinary different derivative, right?
Yeah, ODE, is it?
This is the most, and this is the partial derivative. Okay. So this is our fundamentals, and this is because the reason why I prefer this, and I think depending on that, let me rewrite that del q over del x, because this we'll use it again a lot of times. times dx plus del q xyz t. Make sure that is covering the whole thing. Del y times dy plus del q xyz t over del z dz plus del q xyz t over del t times dt. You see that? So this you can now differentiate with respect to time or space. Suppose I do, for example, let me first do the what we did here, same thing. So if I differentiate with respect to time, I get, yeah, we have to write it out. I like, because we get confused otherwise. Times dx by dt plus del q of xyz t del y dy by dt plus del q xy z t over del z dz by dt. So this makes sure that it's that. Okay. So now this becomes del q xyz t del t dt by dt, which is nothing but 1, right? All right. So now I have that. Now I want to take dq with respect to dx. Suppose I want to do this, right? What happens is dq xyz t, fundamental calculus, del x dx by dx, right? That becomes 1 plus del q, rest of it stays. We have to figure out the rest of it. Del y should be a point. dy by dx, that stays there, plus del q xy z t del z dc by dx, that stays there. Surprisingly, there is another one here, del q xy z t del t. Now I have dt over dx. Inverse velocity, right? Inverse of the velocity.
Oh, yeah.
So you have that. And same way we can do dq by dy. Can do the same thing. dq by dz can do the same thing. Get same thing, right? Except you have to. So this is how the partial and the ordinary differential equations start commuting, so to say. And that's the whole game. Now, this is using the Euclid. Now, if you use tensors, now we have covariant, and like we said before, you have, now that's a little more involved. I think, it leads a lot of things. So the covariant parameter, let's say, or covariant tensor. Let's put it to covariant coefficient. Is Q of subscript mu nu. So where mu and nu are general coordinates, right? May not be orthogonal. Or maybe may not be orthogonal, let's say. So you have, if you do the geometry, this is our Euclidean. You have X, Y, and Z. They are orthogonal, right?
Yeah.
They are all 90 degrees, or pi by 2, orthogonal. So Euclidean, Cartesian. So now if you go to the general thing, the mu could be somewhere here, and mu could be here, something like that.
Okay.
So this is a tensor. And the connection to that baby, if you want to connect with the Cartesian, for example, the mu may look like that. So mu will be function of x, y, z in general, right? X, y, and z.
Yeah.
And so is, let's say, the other one, somewhere, let's say, this is nu prime, which may be another x, y, z. And mu prime x, y, z is non-orthogonal. I don't know how you write that. Not orthogonal to non-orthogonal. So in general, if you take the angle, it could be any angle. Theta, let's say the theta between them, not equal to pi by 2.
I think there's like an upside down capital letter T for orthogonal or perpendicular, but yeah, I agree. I don't know how you'd write that. Okay, so
yeah, may not be a perpendicular to each other.
Yeah, of course. Well, like if you think about it in terms of maybe general relativity and warping of like metrics.
Yeah. Now,
an orthogonal metric, and then when it's distorted, it becomes like a more generalized version of that, but it could still be related back.
Yeah, that's why you have metric tensor and all. So now we have that's a covariant tensor, right?
Yes. Okay.
But now I connect with the non-covariant tensor. I think you can see it, right? Okay. Covariant tensor.
Well, now again, covariant is
the upper script. Again, u and mu are general coordinates.
The covariant and contravariant. Is this contravariant?
Yeah. Now we can have more than mu and nu. Let's say this becomes four things. So nu, alpha, beta, or something. So nu, alpha, beta are general 4-dimensional non-orthogonal coordinates. You see that? So
yes.
And now I can write the connection to contravariant mu prime nu alpha beta. Sorry, I think this is the way it's written. Q prime nu, and there is a lot of tensor calculus. We are not going to. There are a lot of details there. We are skipping. We are doing applied physics more. So we don't worry too much. Let's say G. I think it should be upper script. No, this is lower script. Yeah, because this is the one that's lowering it. It's called lowering it upper and then upping that.
And hiring?
Yeah. Raising it. So
Lowering
or raising.
Right.
This is lowering or raising. So lowering metric, and then you have raising metric. Raising. So G mu this way, when we write it's lowering, it lowers the contravariant to the covariant, right?
Yes.
The raising the metric means G mu prime, and that will convert the covariant to contravariant. So we can write, I think, Q prime of upper script mu alpha beta is the metric upper, the raising upper. This is the raising matrix. This is the lowering matrix. Mu alpha beta, and now we have the covariant thing. Mu alpha beta. So this is our contravariant tensor, and this is the covariant tensor, and this is called the metric tensor. Okay, so I think that's clear. But it's very complex. Now we are getting into complex situations.
Yeah, sure.
About that. So now what we do with that? Now I can go away from the Cartesian. This is a Euclidean Cartesian to a general coordinate system. And now this it is found that use spherical coordinates may be a useful thing. So now, so instead of x, now we define let's go back to our x. So x now is r, what were we called? Sine theta, sine of theta, and y is sorry, r cos theta, right? R cos theta. And that's the Cartesian, Euclidean rotational coordinate. And y is so r is a radius normally. So we have a circle like that. Say XYZ. So now you get into your geometry thing. You are more familiar. So now I have this one is the sorry, this is the radius. And we write this radius. This is the radius r. And now I have the XYZ. So this is my theta. That's how it goes. Triangle. So this is now my r prime, whatever. Let's say it's called r. Yeah, that's the general coordinate. So r is r of theta, let's say 5 gamma, right? That's a unit vector. So so that is considered as unit tensor. So it's called r times the tensor, the unit normal, the n, let's say n, call it n, beta phi r, gamma. Just keep it as a vector now. So that's how that becomes. And then the converting to the Cartesian, you get r sine theta, this simple thing.
Yeah, very good. So this is moving into the more general relativity side of things.
Yeah. So you see that how it became complex. That's what I want to show. Yeah. But I like to keep it as basic as possible. Not jump into that. That's why I want to concentrate on this, because I am comfortable with these, up to here. When you go to the next level, it becomes little uncomfortable. But we have to.
Well, what is the next level? Is that where you're? The next, like.
Yeah,
I don't know. It seems like
digest this one.
You can shuffle terms around.
Yeah. I don't know whether it's too dense or is it getting too dense. Whether we should go in further, but we can discuss a few things. I think if you want.
Okay.
I think things are clear up to this now, right? Up to this year, very easy. I mean,
I follow it to some degree. I mean, obviously, seems to me that once you start getting into this contravariant, covariant thing, I mean, you're still talking about partial differential equations in a sense, but they're kind of masked in this new term notation, and but it seems like you can kind of shuffle them, move them around, and you don't really have to do like that much with them. They just sort of exist. It's a bit confusing, and then obviously when you move into the into the spherical coordinates, that's kind of I mean, obviously you can do even classical stuff with spherical coordinate, like a pendulum swinging or whatever. But I'm not that familiar with all of that side of things with the spherical coordinates. So
there's a Lagrangian. The classical mechanics uses Lagrangian with the spherical coordinates.
Yes, of course. Yeah.
That's an interesting thing. I mean, that's also a good thing.
But what about? I think, if we go back to like the simpler one, like at the very beginning with the spring constant and the angular velocity and all of that, is it possible to make an equation that breaks the system?
Yeah.
Right. So like you can imagine if you have a harmonic oscillator and it's so you have a weight on the end of a spring, but if you were to pull that spring like further than the spring constant or something, would it snap? Or would it give you an answer that for the equation that doesn't make sense within the terms of the equation, or it goes beyond a threshold, and is that something that can be detectable?
We were here, right? This is the one you are talking about. We were here initially, and then we moved on to this one.
Yeah, right? I think so. Yeah, possibly. Yes, that looks right. So yeah, so you understand the question I'm wondering about. If we pull the mass further than the string constant, would that break the system, do you think?
So let me, I think it's a good idea I write it down. Let me see. Yeah. I want to get some kind of an order here. I mean, it's okay. I mean, I can go back to our video and then rearrange them because that's in order. So let me, your question, Christopher. question. What was your question? I want to ensure that I am getting it right.
Yeah, so the question I have is, can we break a harmonic oscillator?
Break
it in the sense that we have a mass.
Okay.
Yeah.
Okay.
We have a mass on the spring.
Breaking the harmonic oscillator. Okay.
Yeah. So
or break the spring, right?
Yeah, essentially, like go beyond the threshold. I'm thinking like going beyond the threshold of the K, like the spring constant.
Okay. Beyond the threshold of spring constant. K, right? So let me just write it. Let me just put a simple figure. You are going to stretch it, right?
Yeah.
So you go back the stretch and then it breaks somewhere. It breaks somewhere. Something like that. Because you are pulling it too much.
Yeah.
So you are breaking it. You are breaking spring.
So that's something to think about. I'm kind of interested in that side of things.
Okay, so what happens there? The force is no longer here. F equal to minus kx, right?
Yes.
This won't be anymore minus kx. That much we can be sure.
It will go positive, will it, or it will?
Yeah, no longer it will follow, because the idea of kx is that you pull it right all the way here. You have certain length, and then you let it go. Suppose you have a weight. Now I let go of the weight. I will again go back to my normal situation. So this is the LO original, right? This is the stretched or expanded.
Yeah.
So LE is greater than LO due to weight, right? Due to weight W. Then LE, okay. So L greater than L naught if W equal not equal to 0, right? L equal to L naught, which is original thing, if W equal to 0, right? It's capital W.
Oh, okay. It's not omega. Yeah.
Not omega. I'll put a capital like that.
Yeah, it's the weight.
Weight. Okay. So what happens is that if the weight is not equal to 0, and you have the stretch and the L, let's say greater than LE, where LE is the elastic limit, right?
Okay.
Let's call it elastic limit of spring. I think that's a fair term, right?
Yeah.
If it is L greater than 0, then spring can break. Spring breaks, let's say. Or L much greater than, let's put it much greater. Okay, because you have plastic and everything, okay? So yeah, elastic limit, then you are, if L slightly greater than LE, then you have plastic extension, plastic extension, or what is called pull out. But again, even in this case, it won't be it will not come back. However, if LE is greater than LE, then the spring won't recover to L naught. Okay. So in this case, F also not equal to minus Kx.
Okay, so that would be the
F
determining
equal to
factor.
Kx assumes that it comes back to original thing. That's what a spring is, right? So
Yeah.
F equal to minus Kx only if L is less than LE. I can put equal, but I like to put less than.
Oh, okay. And let's say the spring goes. You see the way the spring is connected to the board at the top. Imagine
this is
it went
both at the top. Both
yeah.
at the top.
But imagine like I don't know. Imagine you pulled the spring so far and then let go, and it managed to like break through that board. Would that mean at that point
let's
that
do the next one?
F minus equals
another
minus
situation
K
where the spring is
times
breaking down here,
minus
right?
X or something.
Breakout of the bolt or bolt to the wall.
Yeah, through the wall, basically. Yeah.
It comes out, right? So it is free falling now. So you have suppose you have weight here.
Well, I don't know if it's like you've pulled it so far, you let go, and then it goes straight through the wall that it's connected to. So that would be F equals minus K times minus X, would it?
Now you have gravity, right? You have gravity.
Well, we don't even need to talk about gravity, but we probably should later on. But no, not that it's free falling, Rajan. You pull it, let's say, and then you let go, and it goes through the board that it's connected to. So it's
okay. So this is stretching L, and then you have let go.
Yeah.
And then it goes like that, you are saying.
Yes. It goes through the board. So that would be. So that's.
Now,
well, what is the board limit? Is 0, isn't it? Oh no, it's X. So it would have to be minus X.
Yeah,
F
but now it is
minus
not
K minus X.
It is not a good situation, right? This is the wall or a bolt.
Yeah.
Or bolt to the wall. Or roof.
Yeah. The ceiling.
Through the board or roof. Out of the bolt. So this is not a good situation wherein, I mean, it may not damage it. Depends on.
It could still recover, back to its original, or maybe it would have a new string constant.
So now F is.
My guess is minus K, or F equals minus K minus X. My guess.
Something. Plus something. We don't know that.
Is it not minus X though, Rajan?
Huh?
Would it not be minus X?
Won't be minus Kx? Yeah,
no,
if it is positive, large positive, it could be plus something.
Oh, wait a second. If it's minus K minus X, then that would be just plus Kx, wouldn't it?
No. It depends on, this is a spring constant.
Yeah.
Define how you want to define it. And if you plot it, essentially what it is that you are forcing the force. And then X, let's say. So minus Kx means this is F equal to, actually in the negative direction. Let me write it. So we have that F and X here. And then minus kx is it's actually negative slope, right? So it is going like this. This is the slope k minus k minus kx. Should be negative like that, right? At x equal to 0, force is 0. So that's not correct. You have in this axis like this. And F is, yeah, F is a negative force. It's positive here, negative here. So it goes through 0. So F equal to minus kx. So x equal to 0, you have force equal to 0. And then F equal to some value, x, let's say 5 or something. You have the force is minus k times 5. Whatever the k value is, right?
Right.
So this is what the normal thing is.
Yeah.
So now what you're saying is that this is a normal spring. Let's call it normal spring. So now your abnormal situation, let's say we have so now the F could be positive. That's what you're saying. Could be in the positive axis, right? So it could be here somewhere.
Well,
So then this means it is. This means it's not retrieving. It's not coming back to its original situation. Also depends on the position. So here you have this situation, right? Here you have through the board. And you don't have any force now. I mean, no weight. You are not putting any weight. Only the spring is going up like that, right?
Well, why would there be no weight?
When you let it go, you are saying that it pulls the weight also along with it.
Yeah, the weight would go through the wall, through the roof.
So the weight also. Oh, that's because the spring is acting. You stretched it in such a way that when it came back, it's not normal anymore. So this is a breakthrough.
Yeah, exactly. Like we're just asking what the x position of the mass is at time whatever, you know.
Yeah.
After it's gone through the roof, so that would be the x position.
The equation of motion for that. That's more complicated.
Maybe it would be maybe it would just be like a positive x then value. Oh no.
So now we have to find a new force because there is some other forces acting here. So we have to come up with the forces, understand the force, what kind of a force is acting there when it goes through the rod. It's no longer F equal to minus. Here I can write F equal to minus kx. I don't think you can write like that. What is
well,
F?
what about just F equals kx at this point?
F is a function of x. Let's say let F equal to kx, right? Yeah. So this is F equal to kx.
Okay, that sounds.
So this is F equal to kx. So you have positive slope. Okay, and it goes through a 0. It goes through a center, the origin, right?
Yeah.
Because when x equal to 0, F is 0.
So the force is now positive.
Yeah, force is positive. So that is equal to m d square x by dt square, right? So let's solve that. So m d square x by dt square equals kx, right?
Yeah.
So let's move on to the. So md for, I just call it page. Whatever. Page 2. Page 3. So I know what you are talking. The previous one I am not put the pages, but it's okay. So m d square x by dt square equal to kx, right? Now I have to bring it back. So I get m d square x by dt square minus k equals 0. But I cannot use a equal to sine of x. That will not solve the problem. You can see easily why. Suppose I put x equal.
Okay, but that's not a problem though, because like let's say you do well, maybe it is a problem. So, but what will you'll get an answer out of this? Do you think, or will it just give you an answer?
We can solve the problem. I mean, we have to find the right solution. That's so. Let's rewrite this one: d square x over dt square plus k over m. Sorry, minus k over m in this case, minus k over m x equal to 0. So, what is the solution for x that will satisfy this differential equation? The new differential equation. So something that has to the sine and cos. Suppose I say cos. No, cos. Something that will make the second differential equation negative. Actually, yeah. Suppose I put x equals a cos of omega t. dx by dt is minus a sine omega t. d square x by dt square equal to minus, I'm sorry, minus a omega square cos omega t. See, it becomes minus, so I have to get a plus. So I have to get a different. It won't be a simple harmonic. It won't be a cos and sine. I think. Because this and these two have to cancel. If it's a positive, it will not cancel. You have to come to the solution that what happens there, it keeps the thing positive. So suppose I say x equal to a e power omega t, right? So now dx by dt a omega e omega t e power d square x by dt square equal to a omega square e omega t. Oh, actually, yeah, it doesn't matter, I think, here. It doesn't cancel. What we need to find is you get a negative frequency, I think, in this case.
Negative. Interesting. Okay.
Yeah,
So
in this case, so this will be better, I think. Let's see. So let's put that back. Put that back into the equation. These two. So d square x is a omega square e omega t minus a over m a omega t equal to 0. So I can cancel a and a. omega t I can cancel. In this case, it will work. So omega square equal to k over m. Omega is square root of plus or minus square root of k over m. So my x becomes a e power plus or minus k, or I think I have to keep k plus or minus. I get this equation. You see that?
Yeah.
You can solve this like that. Which is a hyperbolic function. This is a hyperbolic, right?
Well, is that not just like, could you rewrite, you see the way you're using it as an exponential term, a power to the exponential, so you could just write that in terms of cos and sine as well.
Yeah, it's exponential. So suppose I plot this one, right? What happens is that, suppose I plot this. So f equal to k times that, right? K times a e power plus 1 minus square root of k over m times t. So f, here I plot k times a, which is a constant, e square root of k over m t. Suppose I plot it with respect to t, right? So we have exponential terms. So either plus or minus, which means suppose I have 0. This is 0 means becomes Ka, right?
Okay.
Suppose I have 1. Suppose it's a positive square root, it become e power square root of, let's say, at t equal to 1,
Well,
1 unit, whatever the unit is.
Sounds like you're getting into complex functions here as well, because you could have a negative square root, could you?
Suppose you have two solutions. One is positive solution. So you have k over m times t. So you have the value here is e power square root of k over m. And you have another term, another solution. Both are positive actually. This, but will be a very small number depending on how it works. Depending on square root of k over m greater than 1, right? Less than 1, this takes over. So this one is going exponentially like that. So this is f equals Ka times e to the power square root of k over m t. And then we have another one here, probably like this, right? Coming here. This is f equals e power minus square root of k over m times t. Okay.
Okay. But I thought, it's interesting at the previous page, when you worked the equation out, it comes out as square root of k over m again. It's the exact same thing as what we had in the normal equation. Although that was plus or minus square root of k over m. But we always chose the plus. We always chose the plus sign. So couldn't we always choose the negative sign for this one?
Because if you use a negative, right? We are talking about omega there. See, that's the difference there. This is not omega per se. This is not the normal frequency.
Oh, yeah.
Okay, the omega is a frequency, k over m.
Okay.
And that's equal to 2 pi nu, or nu equals 1 over square root of k over m. Suppose the other root,
well, there's no,
right?
Yeah.
The other root is mu equals to minus 1 over 2 pi square root of k over. So you have negative frequency.
Right. Yeah. Interesting.
Right? So that's the problem there.
So that would be a
here,
threshold then. If your frequency goes below 0, then your system is broken.
Is it dark matter?
I don't know.
Negative frequency. That's an interesting thing. So does dark matter has a negative frequency, negative energy? Negative frequency means negative energy, right?
Yes.
So that's the question we have. Maybe, yeah.
So, but isn't the system always in a
solution is there? The solution is there.
We talk about,
we are taking the positive in this case, but mathematically it is there.
Well, yeah, I suppose the energy is always in a positive state, but
yeah. We say energy is positive always. Energy, we assume that energy is positive.
But then the force is always this minus. Well, I guess it's like a restorative force, so it always
it's a restorative force, because minus means, suppose I put a spring like this, right? Let me put the spring like that. So restorative is always pointing this direction.
Yes, so it's minus x. Essentially.
Yeah.
In the minus x direction. But yeah, so when we talk about zero force, that's going to be around, well, I mean, zero force could happen at different points along the harmonic oscillator, couldn't it? When it's like fully stretched out,
right?
Huh?
Let's say this is LE, right? This is a normal length, right? L.
Yeah.
This is where the force is 0.
Oh, okay.
Force is greater than 0.
Force. The normal length. Force is 0. So then it goes, it should go negative. The force would go negative past the normal length, as in closer to the 0x value. By which I mean the roof. By which I mean the roof. The force is becoming negative.
Force is actually less than 0, actually, because pointing this way, right?
Okay.
But if it is going here, then the force is greater than 0, right?
In that region between F.
The problem is how it is pointing out. That's all question. So it's positive.
Is that you're saying that the force is positive in the area between the board and the normal length of the spring?
Yeah. So let's write it here.
Okay. So then if the spring goes through the board, then the force continues to be positive. It just grows more and more.
So let's say the spring is here. The force, this is the force, and this is the x-axis.
Oh yeah, sure, Rajan. If you go back to your other diagram where you had the sloping line that goes up to 0 and then goes positive in the other direction.
This one?
Yeah, that one. So when we have 0 force there, that's not the board. That's just like when the spring is at its normal length. So when it starts going, so when the force starts going positive, then that's when the spring is getting more contracted. So
it's actually contracting. See, the thing is that what is happening if the force is positive is that So this is the normal length, right? L0, and I have stretched length LE. Suppose I keep it LE, that's the maximum elastic limit. But then when it goes through the board, sorry, this is where, when it goes through the board here, what is happening is that this length could be less than L0, the original length. So it is shrinking. It is shrinking.
Yes.
So this is the normal length, L0. And you see that it has shrunk. Sorry.
We don't really use the term length in the equation, though. We have the x position, so we would say that the x position is now negative, wouldn't we?
No, this is a force. Yeah, that's true.
Well,
X is,
yeah.
This is the position. So let me put it up here like this. So you have X in this direction. Yeah, actually I should put it like that. Okay. So this is my L0, let's say, right?
Yes.
And then I have.
Is that going to equal some value in x then?
So I stretch up to here, X, LE. But then I make it through the board. So I get, no, it's kind of reduces.
You get a negative length and a negative x.
A negative x. So there is some length, L0 of negative x. So minus L0 prime, let's say, right?
Okay.
And this is positive L0 something, L0 1 or something. Okay. And we say that L0 1 plus, let's say the modulus value of L0 is less than L0, right? Shrunk. Spring has shrunk. So this is the value we get. So this is the total length. So this total length, let's say, is L0 n or something. So L0 n is L0 1 plus minus L0. So I shrunk to length L0 n, which is, so L0 n is less than L0. So shrunk length, original length of the spring. Okay.
Are you taking the modulus, the modulo, because
the modulus is because the total length is positive. You have to add this will be considered as negative x-axis. So if you put L0 1 minus L0, if they are equal, it becomes 0. That's not true.
Yeah, true. So you need the absolute
actual length.
Yeah.
The modulus length or the value, the real value.
Yeah, good point. Yeah.
Magnitude. It's just a magnitude. Yeah.
Very good.
So we have to write like that. If you want to do some equation, we have to take care of all that. Then we can manipulate. We can use it in the equation.
Interesting. So how's your research going on the time loop?
Which one?
the time loop research.
What research is that?
You mentioned time loop research.
Oh yeah. So let me show you some
because I
interesting
think we did a lot on the differential equations there, didn't we? I think we're kind of
I will show you. We'll another time we can go more into detail, but let me show you what I found. Very interesting thing.
Yeah.
Yeah. When I was thinking about the time, because what you said is very useful. So the interesting thing is that the time we said is not non-orthogonal, right? Non-orthogonal axis.
Oh, okay.
So what happens is that why it has more than 3 dimensions, things like that. So if it is non-orthogonal, the x and minus x, right, are not the same, not collinear. So normally if it is x and minus x, it's collinear, right?
Yes. Yeah, so you're talking about
non-orthogonal means curved, right?
Right. Yes.
Curved axis. Then they are not orthogonal. So which means that this is not the same dimension. So I have to count it as one dimension, another dimension.
Right.
Then 3 and 4, 5 and 6. 5 and 6.
But you can map that to a Cartesian coordinate system, can't you?
No. So we get what I call as chandelier. It looks like a chandelier.
Yes.
It looks like a chandelier.
Or like an umbrella, like you're talking about it.
Yeah, umbrella or chandelier. So if you are on top like that, you put it up there, right? The light. It looks like that.
So are you saying that you cannot map that?
Umbrella.
Are you saying that let's say you could work, I don't know, maybe with spherical coordinates in that system? Couldn't you map that back to Cartesian coordinates then afterwards?
Yeah, that's exactly what we have to do. That's why I use spherical coordinates. You remember the transform I use as spherical coordinate?
Yeah.
Because
okay, yeah. So fair enough. So you could map it into a Euclidean space. How many dimensions would that Euclidean space have to have?
Euclidean means you have to consider like a polar triangle. You know what a polar thing is, right?
Yes. 90 degrees at each side, each corner.
So if you are polar, you can get 90 degrees for this one.
Yeah.
Polar triangle. I have not looked into that, but I was thinking about it.
Well, that sounds like you're in hyperbolic space then. You've got...
Yeah.
Yeah. Okay, fine. That's no problem. So you're in hyperbolic space, not Euclidean. So it'd be a bit difficult to map it to Euclidean. There is a way to do it, but we won't get into that now.
For Earth, that's true. Suppose you are Earth, right? You have the longitude, which is the timeline. This is polar coordinate. Called polar coordinate. So you have north and south here. Yeah. North and south, and your equator here. So this is your latitude. That's let's say space or spatial. Now this is longitudinal. Which is time or temporal.
Okay, but you seem to be talking about multiple time axes, so you could have both latitude and longitude as a time axis.
So that helps in, for example, Earth is rotating around, right? Other systems, solar system. So now you have one for this one, theta for this one, another rotation called phi, and then the whole Milky Way is kind of rotating around.
Oh yeah. Well, you might need to go there, but yeah, I see what you mean, though.
Yeah.
But even if you end up higher to like the universe, because time is running throughout the entire universe, isn't it? So
yeah,
you could have the hypersphere as this ball that you're looking at.
yeah,
As time runs through the entire hypersphere, and then
yeah,
you could have you could have it where you could have time rotating on the sphere just as a single longitude point, a line that just goes around and around and creates all of time. And then you could have an infinite number of those as well. So you could have different multi-dimensions all on the same hypersphere, which would be nothing and compact. So
let's consider your what you call your hypersphere. So you have flat space, right? And you have something that's rotating like that.
Right.
And this is rotating.
Huh? Well, if you have this thing going around like at the speed of light, it's going to length contract, so it'll just be a single line. But within that single line is the entire universe.
I mean, you are projecting it right onto the thing.
Well, no, but like even just ignoring the projection for the minute, if we have the entire universe and it's rotating around the sphere at the speed of light, it would be contracted into a single line. So the entire universe. So you could like have an infinite number of universes on the sphere, all rotating. So that's pretty cool. So then you could it'd be like you just tune into which frequency you want, and then you project that entire universe onto the tangent plane. So you could have an infinite number of universes, right? What? Yeah, an infinite number of universes projected to the tangent plane, like changing the channel on a TV screen.
Yeah, rotating their own speed at their own.
Well, I think they might all be rotating at the same speed in order for it to be length contracted.
Or same as the light, right? Same as the light speed.
They'd all have to be traveling. I think they'd all probably have to be traveling at light speed, but who knows? I mean, they could be going at different light speeds in a sense, if that was possible. You know, if the speed of light can be different speeds, maybe, and all length contracted, or maybe they don't all have to be. But I suppose if they're different frequencies, if they're different sizes, that might also keep them separate. You know, the way we have multiple channels all in the same frequency band kind of thing, or spectrum.
Suppose it depends on epsilon mu naught, right? If it is different.
Are you talking about relativity and? Oh, okay, yeah, I see what you mean. Interesting.
Varying in different spheres.
Yeah, assuming those laws work on the scale we're talking about, but yeah, they probably we should assume that they do and work with them. That makes.
So this is the permittivity of free space, and this is the permeability, right? Free space. So this is the free space. So your free space has to be different.
Yeah, there would probably have to be some difference. Yeah, we could look into that. I mean, this is kind of something that I haven't really.
Yeah, this is something we have to think further.
Yeah,
I mean, it's something that has come up today. So
that's true. I mean, if you think about, you could have like two. I think we spoke about this before. I brought this up before that. And a lot of people talk about this idea of two time axes that are orthogonal to one another. So if one is the real number line, so it's time, just normal time stretching forward and backwards, and then the other one is right angles to it, and that's imaginary time, then that creates a plane of time, doesn't it? But the interesting thing about that is that that's a complex plane of time. But the thing about the complex plane is that it's non-ordered. So if you have a sheet of time, it's going to be, there's no actual order to the events on that sheet of time, which makes it eternal in a sense, because time is not flowing there. It doesn't flow forwards and backwards, either in the imaginary or in the real time. So that creates it. So that could be like eternity, but then we'd have a third time on top of that, I think, because you know, someone was saying, well, if you have eternity, then there's you know, like there's no space and no time. You know, where you think about God exists outside of time. So in eternity, there is no time. But I don't think that's necessarily true. Like, but we can imagine it like, let's say there's a moment, like yesterday at 3 o'clock. Okay, whatever event happened then, we live. Let's say we can move across the plane. Yeah, so we can walk. We can walk to the to 3 o'clock yesterday and just visit that time, and then we can leave that time, and then just later on we can walk back. So now we visited it twice.
See, I came up with a general solution for time. Can you see this now?
Oh yeah, I can see it.
Yeah. So this is what I am. You know, when I research it, I find you can define a 4-dimensional time like this, where S is the action. Action is called the action, X. Yes. And X, mu, and everything are the space-time coordinate. Okay.
Yeah.
I am still deriving it. So this one is like a 4-dimensional thing, but you can convert to a chronicle delta Levi-Civita symbol,
right?
Like this one, with the energy, angular momentum, and entropy, things like that.
Yeah.
I not operated on this. I'm just pointing out here.
Okay.
This is my old one. You know, but I show that one.
Yes.
The new paper, I'm putting it now. It's a revised thing for the paper.
It looks good.
So the time, this is called algebraic time. The algebraic time. T is the algebraic time. I say that there are 2 types of time: arithmetic time and algebraic time.
Oh,
the arithmetic time is scalar. When this is 0, t omega, this becomes 0. They just become a scalar quantity, right? A constant. That's what we are using now. But if it's not 0, q mu alpha beta is not 0, then you have the time like this, and we can extend to up to 6 dimensions if you want to.
Okay.
When I do the operation,
sorry, Rajan, this is a little bit. I'm only up to 3 dimensions of time at the moment.
Yeah.
I don't know where you're getting your 4th dimension.
Just pointing out that. Yes.
I'm not saying it's wrong. I don't have a concept of what the 4th dimension of time is yet.
Yeah, I'm just pointing out. I'm not saying that, just to point out that.
Yeah, it looks good though. I like. You should. Yeah. Can you send me that on when you're finished with it?
You have to come back later. What I showed you here.
Yeah, it looks really good. Yeah.
Yeah, this is what I have to work. I finish and send, and once they accept that, that becomes part of the publication. We'll come back to the later, but I'm going to work on this one.
Yeah,
how to convert to polar coordinates. Polar coordinates, and how do you get the dimension? Right, 6 dimensions. If you convert to polar coordinates, then this is minus x, and x, let's say, becomes. And all other things becomes reasonably. They become 90 degrees. They get dimensions. Then you can use proper dimensions. Right? Because dimensions mean they have to be orthogonal, right?
Yeah.
So,
well, unless it's
use a polar triangle, we can make it orthogonal, and then
well, didn't we have a big debate?
And then we have proper definition.
Didn't I have a big debate with Christian about about 6 dimensions and how you could compactify them all into into 4 dimensions. I think it was using stereographic projection. I'm gonna have to revisit that video to see what we were talking about, because it would be interesting if we could do the same thing with your 6 dimensions of time and see if we can reduce them to just like 4 or 3 using stereographic projection. It might be interesting. It might give you know, it might result in some something.
I just write down your question. So reduce the 6D
reduce the number of dimensions. I think we could reduce them from 6 to 3 using stereographic projection.
What is called polar manifold. You have to call it polar manifold, right?
Using stereographic projection, though.
To stereography.
Yeah, it should work. Technically, you'd need 4 dimensions to do it, but you'd only wind up with a 3-dimensional manifold, I'm thinking.
So you can have 3 dimensions of space, right? 3 dimensions.
Yeah, 3 dimensions.
And time, you add 1 more dimension?
No, you'd start with your 6 dimensions of space, but we could compactify them to just 3 on a 4-dimensional manifold. And then that would coincide with
4-dimensional space and then 2-dimensional time?
It'll be a 3-dimensional manifold embedded in a 4-dimensional space.
3-dimensional time manifold.
You'd have all 6 of your time dimensions on the manifold, I think. Well, yeah.
4 plus 3 is 7. 4 plus 3 is 7.
3, 7?
No, 4-dimensional space, 3-dimensional time becomes 7.
No. Like this is more just how do you say? This is mathematical. So we'd be talking in time dimensions only. Yeah.
So 4-dimensional space.
I mean, yeah, you can technically start bringing in the 4D space, and then what did you? Would that not be 12 then? Oh no, it's supposed to be 7. Yeah. I mean, you could go. Yeah, you could go further then and turn the sphere. You know the way you started talking about rotating the sphere. You could rotate that into a donut. You know, like a torus, and then that would add an extra dimension. So you could go back up to like 6 dimensions that way. Could be interesting. You could even go. You could even go further. You could go to like some sort of Lorentzian lattice and go up to like 26 dimensions, like they did with string theory and stuff.
So it's all curled up dimensions.
Yeah, but they wouldn't need to be small. They're actually way bigger than the universe, these dimensions, because they exist outside of the hypersphere. They're enormous.
Yeah, you are more familiar with the geometry. So once I finish this, I'll talk with you because you have better understanding of that.
Maybe yeah, it'd be really interesting to. I'd like to work with you on that and see if we can kind of jam on the theories a bit and get some.
So I'll
work together and see if we can join the theories together in a way that's interesting and fun and but doesn't like reduce what you're doing, but sort of like compactifies it, but doesn't take away from it. That'd be cool. Yeah, I'd like to work on that. Also, I'd like to work more on the time loop because have you looked in? Did I show you that guy's work, Terence McKenna's Time Wave Zero? Remember, I showed you that book called The Invisible Landscape.
What is it called? Time loop.
It's called The Invisible Landscape.
Invisible.
And in that book, he has a lot of mathematics worked out for this thing called a time wave zero, which is essentially a time loop.
Or time loop.
Yeah. So after we're done with because obviously you're busy with this 6-dimensional time thing, and you're working on papers on that and other things. So, you know, maybe we can work on the time different. This is a different version of the time loop, or a different way into it, I think, and it could produce really good results. So, you know, if you have time, look into that and see if you can get your head around some of the maths. I'm pretty sure.
Some interesting thing I came up with again. Let me briefly show about the time loop thing.
Oh, great. Yeah.
I have a lot of things. I mean, I don't know how long it will take to put all these.
Yeah, this is it. We have so many ideas now that, like, I don't know. We need to employ people to do the work for us at this point.
Yeah. That's why I want a world university where we have people full-time working. We have to get funding for that.
I suppose one way to do the world university would be online, because getting a building and insurance and all of that is just mental, isn't it?
Oh, yeah. Yeah, I mean, eventually it will be online, but we have to have yearly in-person meeting kind of. So we go to the things and then we are on the same page, that thing.
I suppose you get you could have. That's true. I mean, although we wouldn't all have to be on the same page, would we? In a university, I think there's always people on different pages in universities, isn't there?
Yeah, but you know,
but I agree. It'd be good if you know the way if you have like an institute or something where everyone's working towards the same goal. I like that idea.
That's what
I think, you know, you've had your ideas, and then I have mine, and we all have different ideas. But it's cool when they start sort of coming together, and you go, oh yeah, you can join that to this way.
I agree.
Yeah, that's good. I'm more in favor of that. But if it's not a thing, like if it doesn't exist, then you can't force it. But it seems like there's a way to do this now, so that's exciting.
See, one result I got, I'm trying to show that one interesting result.
Great, yeah. And so, what are you basing the time loop on? Is it 6-dimensional manifold time, or is it something completely different?
So right now, I'm just using time as a tensor, like I showed you. I can fold everything back to a tensor, and the tensor will have 6 elements, like, you know. So I fold everything. So
okay, cool. Oh, that's interesting. Yeah, 6 elements. Yeah, very good.
So if I want to show this one, what I find, and this may be the upper part of the discussion. Again, it will be much later. Let's see. Okay. So I have, let me
interesting.
So let me pull up this one, my other screen.
Oh, you're already on, so we'll just make it bigger.
Oh, yeah. Okay.
Order, steps, filter, and complexity.
This order comes from chemistry. Okay.
Oh, cool.
And this complexity comes from the physics.
Right. Okay.
Okay. So your order, this is the ultimate thing. So
yeah,
I found that typically, I mean, this is my conjecture, or complexity you can define like filters. You can think of that, you know, like a picture. And order depends on the steps, because reaction steps, things like that, right? You have multiple steps. That's when the order comes in the chemistry. So when I plot this one, it's a very conjectural plot. What I see in time loop, like, let's say it's 1960.
Yeah.
And it started, I had probably pretty close to what it is, because I checked with some observations. it went through this type of thing, and then like this, and then when that comes back, this is 2040. So this could be somewhere in 2000s. So we may be somewhere here. We don't, we have a lot of conflicting information. So that's why you cannot put it 2020s. This means we are climbing up, the steps.
Yeah.
And then we come back here, the steps in 2040. The cycle continues.
Yeah,
So
yeah.
like in 1980 or 1990, we are climbing up the steps. So this shows the why we have so much of problem. Like in 2001, we are, and then we are here. Suppose we are here, we have to yoke out. I'll call it yoking out. You have to really climb back up. So you can connect with this one to Bohr line.
Okay. Well,
so
let's keep it a bit simpler first, because we need to work out the total, maybe the shape that we're going to use for the wave, and then I'm thinking Terence's wave is probably the one we should use, because it's just the best wave out there. Have you looked into Terence's time wave zero?
No. We'll compare it. We'll compare it eventually. I want to do as many ideas I have, conjectures, and then check, because I don't want to be what you call biased by the. If I see something, right, I could get biased. I don't want that. I want independently to work.
Have you seen?
At some
Did you ever see the work I did on the?
We'll compare.
Yeah, I did a time loop website a while ago.
I think I have it. I had to check.
It's in the book that I think I gave you a book, and in my book called is it called Cataphysics or Siempre Brocade or something weird like that? That book has a time loop in it. I gave you the PDF, and it's based on the days of the week, numbers, and it works out anyway that there's a chemistry thing involved in it to do with the rate of carbon decay. So like carbon isotope, what is it, carbon 14 dating or whatever it is. So carbon 16 or carbon 14, but it works out at like 56,000 years, which was how long it takes for the sequence that I developed to repeat.
Yeah, the tree, right? The tree. Yeah. The tree. Age of the tree. Age of the tree.
Carbon dating age of the tree. Carbon 14, I think it is. Well, it's an isotope, and it decays from carbon 14.
Yeah, that's how they find the age of the tree, things like that.
Yes, exactly. So it was just an odd coincidence that the sequence of time that I developed worked out at 56,000 years, which is also equivalent to the time it takes for carbon C14 to decay completely. So that's interesting in terms of your chemistry models. Perhaps there's loads of time loops, each one dealing with all of the different isotope decay things. So that's something to look into. But also there's another thing, right? Because you mentioned the number 6, and then recently I've been looking into you were talking about this before as well. Isotope, isospin, and hypercharge. Have you looked into those issues?
Isospin, hypercharge.
Yeah, isospin is how the electroweak force connects to how the weak force connects to the electromagnetic force, right? Or if it does, and that gives you that gives you values for isospin. But then if you minus the isospin from the charge values, you get hypercharge values. The interesting thing about those hypercharge values is that they run from as like 0, 1, 2, 3, 4, and they skip 5 and they go to 6. Yeah, so there's no charge that is value 5.
0, 1, what?
2 all the way up to 6, except leaving out 5. 0,
1,
1,
2,
2,
3,
3,
4,
4,
6, then
and then 6. Yeah, so there's no 5 in it. So that's interesting as well, because if we go back to Terence's time wave, he worked his time wave out by looking at the different number of lines in these things called hexagrams, which are a type of Chinese divination system that was thought up maybe in 2000 AD, 2000 BC, sorry. And so about 4,000 years ago or something like that. And then in that system, he also found that there was no difference of number 5 in the whole sequence. So there could be a relationship between hypercharge and the I Ching time wave. So that could be an interesting angle to look at as well.
Group theory also says this is a 5th dimension is what you call not a real time. Not a real, not 5th. No, the symmetry, 5-fold symmetry.
Oh yeah,
is not non-real.
Oh, that's interesting. Yeah.
Yeah.
Although
group theory, crystallographic group.
But didn't what's his name then? Roger Penrose discovered.
Yeah. You were saying that before, yeah.
Quasi-crystals. Yeah. But then they're interesting because those quasi-crystals are actually projections of 4-dimensional geometry into 3-dimensional space. So it's interesting that group theory would say that they're not real, and in a sense they're sort of hyperdimensional. So that's interesting. Yeah. That's another area of research. So, but so it seems like you can take these 6 hypercharges and all of that, and you could take the some of the what are they called, particles associated. So I think you have to take the quarks and their color charges, and then the charged leptons and non-charged leptons, and you can put them all into this group theory, a group called SU5, and the exterior algebra of that has 2 to the 5 dimensions, so it's 32 dimensional. So the number of 5, even though it's left out of the sequence, is important through on a larger sense, which I think is interesting. So
another thing I found is you remember I was doing earlier the group theory, field group theory from my thing, and then I made a presentation, and you and Christian commented you have to take into account charge and mass and everything.
Yes.
So when I did that, I also I find that you have to have 8 8x8 matrix. So
right, okay.
And I checked in the website also. Is it a possible thing? They said that people are not like standard model SU1. Then you have SU2 or 3. And
so
then
U1 cross SU2.
You have SU up to SU4. You can do up to SU4.
That's right. SU2 cross SU2 cross SU4. But you can also go up to SU5, yeah?
Yeah, but not. So that's where people are stopped. But they said that 8 is a definite possibility. There are. I think it's a good idea. I checked somewhere.
Will they do something with E8?
So we can actually come up with this stuff. Remember?
Oh yeah, it's a good idea.
This is like a point particle. So each 8 different particles. Okay.
Yeah.
Point particles.
Well, actually, if you look, there's a guy called Garrett Lisi, and he does stuff like this. He has the E8 model, and each coordinate in the vector for the coordinates for the points is like, one of them will be the mass, one of them will be the hypercharge, You'll have the
here
charge.
it will be like that. There'll be charge. This is the symmetry group.
Yeah.
Charge and mass here. You will have charge and mass, and then you have the wave function here. Symmetry, psi symmetry. This is the modified wave function.
Very good. Yeah.
And then you have fields. So the field is considered here. So finally, what you get, simplify, you get something called a point. This point, because when you simplify, you get a simple point. But this point is like it can collapse. It can collapse or it can expand. Okay, if it collapses, it becomes like a 0 point. If it expands, it becomes like an inflaton on infinity point. So it looks like a twinkling star, twinkling star.
Well,
so this point,
yeah. So, and that's quantum? Is it that thing, or is it?
Yeah, this is a quantum because this is the commutator. The normally, when you do a Bra matrix and a Ket matrix,
you get, of course. Okay, very good. Yeah.
The Dirac thing, the Dirac or a Kronecker thing.
Yeah,
so that becomes
one point. Have you looked into my research on the what is it called, the 600 cell and all of that? Because I did a grand unified field theory with the weak force, the electroweak force, the strong force, and the electric force. I think I have gravity in there as well, but it's not like, it's not like it doesn't give you any major revelations about gravity, I don't think, as far as I recall. And there might be, if there's another 8, there's 8 particles that are kind of unaccounted for. So I called them all 8 gravitons, but they could just easily be like 8 other particles that no one knows what they are. But the thing is, you can take the 600 cell, which I think has 120 vertices in it, and then if you take the joule of that, but not the 120 cell joule, but just a different kind of joule that's based on the 24 cell, and if you take that joule and then match all of those vertices together, you'll get something that's equivalent kind of in terms of symmetry to E8, which is 240 vertices. And then if you could expand that into 8 dimensions, so you could, that might be a way that you could work. That might be a way that you could, with what you're doing. Obviously that's kind of difficult.
Work together on
pretty difficult, but
on E8, right?
I got up to a certain point with that, and then I've kind of switched into cosmology at the moment, but I didn't realize that I actually had a grand unified theory until I kind of noticed that whole especially the issue to do with isospin and hypercharges. And then I noticed that that model actually does kind of work out fully, although just like these other grand unified field theories where they try and put let's say the standard model into SU5, it turns out that there's 6 ways to do that, and in my version there's 12 ways to put all the particles into the 600 cell. So that's kind of cool, though. It doesn't really bother me.
So
I think those degrees of freedom might be important in terms of how things transform. If you don't have degrees of freedom, then everything's very static. And
this is dynamic. Actually, you see every point can be inverse transform. You get this one. Every point will be like that. Each point, each particle.
It'd be cool, though. It'd be cool if you could, when you're working with those 8 vectors or whatever. If you could tie it into the research I did, because I think what I did is correct. Or you can tie it into Garrett's work, but I don't think Garrett's work was correct because he wasn't able to fit all the particles in, whereas I was able to do that. And I also got supersymmetric particles. That's the only issue. So if you bring E8 into it, or the you know, how do you say, an isomorphism of E8 using the 600 cell, then you will get all of the particles in the standard model plus these extra 8 that I'm talking about, and all of the supersymmetric particles as well. So, which haven't been discovered. So that's a bit of a problem with the E8 model, but yeah, look at it. I have all of the stuff is on ResearchGate, and it's pretty comprehensive in terms of which particles match with which vertices, coordinates, and obviously which forces. The forces are kind of outside of the model in a sense. They're like, they come from the interrelations of all of the particles and geometry. So yeah, so loads of stuff there, Rajan. We'll probably have to call it a day because
So yeah, we had a long time today, close to 4 hours.
It was very productive though. So
we went through a lot of basic things. That's good. Thanks.
Great. Yeah, hopefully now we'll keep up the momentum and the how do you say that, the harmony of concepts that come out of it. That's important. Okay.
Okay, have a nice week, and then we'll see you next week.
Excellent. Okay.